This problem is a quadratic equation problem, and specifically we're going to be working with what's called the position function. The position function, if you've studied algebra much at all, you've seen this. It's a function that tells you the height of something when it's been dropped or thrown up into the air, and gravity is now going to pull it down to the ground. There's three terms in this quadratic, and they all specifically mean something. The first term deals specifically with gravity. This negative 16 comes from the acceleration of gravity, the negative because it's pulling it down at 16 feet per second. The 48 here, this comes from, in the generic version of the position function, this is the velocity component. We always plug in the initial velocity. And this, in the generic version, is what's called the initial height, how high off the ground did it start. In this problem, a baseball is thrown upward from a height of 6 feet, so that's going to be our initial height, with an initial velocity of 48 feet per second. And the height is given by, again, here's the height, at a given point in time. We're looking at between 0 and 3 seconds. If you're told that it reaches a height of 64 feet, is this possible? Well, this is a quadratic equation. We have more than one way to actually answer this question. I'm going to actually work it in 3 different ways. The first way I'm going to do this is I'm going to just let my height be 64 feet. I'm going to plug this number in right there, and I'm going to solve this. So I put in my 64 feet, set it equal to the position function with the specific initial velocity and initial height. Again, these numbers change for pretty much any time you work one of these problems, because it depends on how fast they throw the ball or how high off the ground they are. To solve a quadratic, typically what we would do would be to set it equal to 0. So I'm going to subtract 64 from both sides. That's all I did here. And this ends up being a negative 58 when we do that. Now, we have lots of ways of solving quadratics. We've got factoring, we've got the square root method, we've got completing the square. With the position function, I almost always go straight to, I always go straight to the quadratic formula. It's just much easier. You almost always get decimals, and trying to factor with decimals can be very difficult. So I'll be using the quadratic formula. To remind you of the quadratic formula, it's x equals, I know I've got a t here because we're talking about time, but the generic one, there's an x here. Negative b. The b is right here, the coefficient of the first degree term, plus or minus the square root of b squared minus 4a, the a is the coefficient of the squared term, times c, the constant, except in this case I've got to use this one, all over 2a. Okay, and again the a is the coefficient of the squared term. Well, you start simplifying this a little bit, and soon you're going to run into a problem. Right here. I went ahead and squared that, I multiplied these together, I went ahead and subtracted, and now we've got a negative under a radical. We can't solve that, not without imaginary numbers, and in this case we're not dealing with a situation that we would use imaginary numbers. So right now I can answer the question. Can I say that it reaches 64 feet? No, it's not possible because we run into imaginary numbers right here. So there, I finished the problem, but I told you I was going to work it in 3 different ways. So that would be one way you could do it. Here's another way you can do it. You can find the vertex of this parabola. Quadratics are always parabolas. We have a little formula to find the x-coordinate for the vertex of a parabola. It's x equals negative b over 2a. Again, I'm going to go back to plugging in that negative 48 for the b and the negative 16 for the a. Same a and b as before. This tells me that the time, I switched from x to t here to be specific to this problem, the time is 1.5 seconds. So 1.5 seconds after this person throws the ball into the air, it reaches the highest point. Well, we don't know what the point is. So all I'm going to do is I'll plug in my 1.5 into, now I'm going to plug it into this equation up here for the t's. So I plug those in, I evaluate, and I get 42 feet. So the highest it goes is 42 feet. That is another way I could have answered the question. So no, it doesn't get to 64 feet. The third method, simply graph it. I graphed it out. I did have to actually use my time for the maximum height and the maximum height to get where the vertex was. I could have estimated it by looking, but now I know it's at 42 feet. So a graph in this case could also answer the question.